Hello everybody. So today we are going to continue where we left off in the last class, which is our discussion on aberration and how it can affect the quality of the image that you're trying to acquire. The last thing we want to talk about is astigmatism, and as we mentioned in the previous class, astigmatism generates from imperfections in the quality of the coil or the winding or some contamination that might have come into the electron column, right? So the effect of astigmatism is such that it distorts the image. So if you were to image an object, you ideally want the probe size, the probe of the beam that is falling on your sample or the specimen to be a perfect circle. But if you have astigmatism in your column, what happens is that circular beam profile is not there anymore if you go in and out of focus, right? So while you're imaging, if you want to figure out if you have astigmatism or not, is to try and focus the sample the best you can, and once it's in focus, you deliberately go out of focus on either side. And while you do so, if you find that the object or the image is getting distorted, well, you would expect it to blur as you're going in and out of focus. But along with the blurring, if there's a distortion or the object gets elongated along a given direction, that means you have astigmatism. And by default, any image you try to take at the very beginning will be astigmated. Okay, so let's try to understand what is the origin of this. Now, if you have an imperfection in the coil through which your beam is passing, all the different lenses that we spoke about, it so happens that the electron beams coming in two different planes can have different focal lengths, right? So you can see that here in the image. The electron beams traveling along this plane cross here, so that's the focal length, but the electron beams traveling along the other plane have a focus somewhere here, right? So there's a delta FA, which is the difference in the focal length, as a result of which you have the astigmatism. So how you can counter this is by using the stigmator coils, which is basically an assortment of 8 different coils that apply tiny magnetic fields to distort or to deflect the electron beam in such a way that you minimize the delta FA, right? You minimize it, and that way you're able to get rid of astigmatism, right? So let's take a look at the quality of images which are astigmated versus a good image. So here is what I was talking about. You have a circular profile of the beam, right? And because your image is astigmated, although you try to get the best focus, you have a blurry image. Now, if you use the focus knob on your electron microscope and you overfocus it, because of the presence of astigmatism, the beam profile from a circular patch changes to an elongated ellipsoid, and you get these elongation in the image itself. On the other hand, if you underfocus it, the elongation occurs at an orthogonal direction, and you have now distortion in the orthogonal direction. So if you are able to get rid of the astigmatism using the stigmator coils, then when it is focused, you get really crisp images, which is what you want, right? Now, in the focus state and in the condition where the astigmatism is completely removed by those stigmator coils, now if I were to go out of focus, go in and out of focus, these objects ideally should not show any elongation in random in directions like it is shown in the images here, right? So if I were to go out of focus now in the focused condition, it would just blur and then come back into focus as I bring the microscope back in focus. Okay. All right. So now that we have figured out the different kind of aberrations that are possible, and we have discussed about the kind of electron guns we are using, the electromagnetic lenses we are using, the final thing we want to talk about is the quality of the probe beam that the specimen encounters, right? And I touched upon this a bit in the last class, where I said that the probe beam is Gaussian in nature, and you can use the full width at half maximum of that to determine the probe diameter, right? But that was without considering any kind of aberration. Yes. Now let's take into account the aberration itself. So DG is what we discussed, or we have been discussing in the last few classes, which is the Gaussian probe size of the beam current incident on the specimen, and that is related to the brightness equation that we encountered in the first class. Okay. Now D of DS, DD, and DC are the respective aberration from spherical, are respective aberration due to spherical aberration, aperture diffraction, or chromatic aberration, right? I hope you can recollect all of this that we discussed in the last class. Okay. So now if you were to take the effective diameter of the beam, you're going to take the square of the different aberration and then take the square root of that, and that will give you the diameter of the beam because of the inclusion of these aberrations, which is in addition to the D of G that you have. That is what we discussed in the last class. Okay. So now if you were to plug these relationships into the equation here, you will end up with the equation over here on the right hand side. But before we get into that, let's just do a quick recap. So here is your brightness equation, and we have already seen these equations in the last class, where dG is inversely related to the brightness and is directly related to the probe current. Okay, so if you have a larger probe current, you have a larger probe diameter, right? So you can rewrite that equation here, where the probe current is directly proportional to the brightness. That is quite expected. Now you take the D of G and the aberration relationships that we saw in the last slide. You plug them in here, and you get the relationship that would describe the beam profile or the beam diameter, while you take into account all the different aberrations. Okay, so what we are trying to identify here is what is the optimum aperture size for maximum brightness and the smallest probe diameter. So the motivation here is that the smallest probe diameter would enable you to achieve the highest resolution in imaging. Yes. So you basically do some math here. So you take you rewrite the equation here so that dg square is now dp square minus ds square minus d of d square, and we are getting rid of the last term over here, which is from the chromatic aberration, because at high accelerating voltages you can kind of neglect that value. It becomes insignificant, but it does have some role to play at low acceleration, and we may discuss about that later, if time permits. Okay, so you take this equation and you rewrite it in terms of I of P, right, which is your probe current, and you take a derivative of I of P with respect to the convergence angle alpha, right? If you set that to 0, that means at that probe angle, your probe current is not changing, right? If if dip over d alpha is 0, that means at that condition you have maximum brightness with in the smallest probe diameter. Okay, so if you do the math, you will end up getting these relationships where alpha optimum is the optimum aperture angle, where you have the maximum brightness for the smallest probe beam. Okay, and then you can plug in this into this equation here, and you end up getting the minimum probe size, which is d min, and the I max, which is the maximum probe current you can expect from your emitter. Okay, so here K is a constant that is almost unity. You have d min, which is in nanometers, lambda is in nanometers, and the current is in amperes. Okay, so points to take note here are that the minimum probe size depends on the brightness. So if you increase the brightness, the probe size goes down. That is evident here because the brightness is in the denominator and your probe is on the numerator, right? And then it's directly proportional to the wavelength, and it increases with spherical aberration. So if you have higher spherical aberration, then the beam spot is going to get broader, and that makes sense, right? So you want to minimize the CS to get the minimum probe size. Okay. All right. So at this point, let's go back to this slide where we have seen this before. We have spoken about the electron gun, the emitter assembly, the different kind of condenser and the objective lenses. Now here you have the either the pinhole or the immersion lens. What we did not talk about are the scanning coils, and we'll see what role they play. And essentially, at the end of that, we will have, once we discuss this, we would have finished everything we need to know pretty much about the electron column itself, right? So let's take a look at the imaging process and what role these scanning coils play. So this is the inside of your pinhole lens, and the scanning coils are placed about the stigmator coils, right? So here is a magnified image of that. What essentially happens is, we spoke about this very briefly in the last class, you have the electron beam which is incident at a given spot on your sample. Now that beam needs to be moved along the X and the Y direction to obtain the rastering scan. That is the role of this purpose of these scanning coils. So you have the first set of scanning coils that are responsible for motion in, let's say, the X direction, and then the second set of coils are responsible for the deflection of the beam in the Y direction, right? So you apply small currents to each of these. The amount of current that goes into this coil, these coils are already pre-programmed. They use digital to analog converters to get the appropriate deflection, and essentially you move each time. As you can see here, you have these different squares that represent the motion of or the rastering motion of the coil of the electron beam to generate the image. Okay, and these coils also determine how you control the magnification of the imaging process itself, right? So what is magnification? That magnification simply means it's the length of the scan on the monitor or wherever you're acquiring the image over the length of the scan on the specimen, right? So this scan is the scan that is determined by the deflection from the scan coils on the specimen. Okay. Now usually what happens is the length of the monitor is constant, right? You cannot change that. So the magnification is determined by how much current you put into these scan coils, and also it depends on the working distance itself, right? So this is just a schematic of two different cases. In this case, you have a larger working distance, W. A smaller working distance, and here you have a larger working distance. So if the sample is closer to the aperture, then the amount of deflection you need from the scan coils is going to be less. That means you're scanning over a smaller area, but the image is formed in the same monitor, versus here you're scanning over a larger area, right? If the working distance is higher, and now so essentially for high magnification, what's ideal is that you have a shorter working distance, and the shorter working distance also minimizes aberration. So you have higher quality, crisper images, right? Because if minimal aberration means you have a smaller spot size. Make sense? So if this is a chart just telling you, giving you an idea. So if you a 10x magnification means you're scanning on the sample itself about 10 millimeter by 10 millimeter. Okay. Whereas a million x means you're scanning over 100 nanometer by 100 nanometer on the sample. Okay. And finally, let's take a look at the real device itself, the electron microscopes, the insides of it. The image on the top on the left shows the sample chamber that has been pulled out of the from under the electron column. Some of the older models do this, where the entire thing comes out of the column, where you load the sample and then you push it back in and you pump down. But the newer models have something called a load lock. It's a bit difficult to explain that over a video, but I might be able to show you some YouTube videos in class later on to show how the samples are loaded into the chamber. Okay, and inside the chamber, here what you're looking at is that pinhole lens, right? And this is the sample where you place the sample. So if you have these little metal discs on which you mount your sample, and then you bring it right under the pinhole to image it. Okay, so at this point we have reached from the electron generation all the way to the electron falling on your sample, right? So this was pretty much an engineering discussion so far, with some fundamentals of physics that went into the development of the engineering equipment. Now here is where we get into a bit more of the physics, where we will discuss a bit about the electron specimen interaction. There's going to be elastic and non-elastic, inelastic interaction between the electron and the specimen, as a result of which there will be X-rays generated. And then once we understand what that interaction is, then we are going to talk about the detectors, because the detectors are essentially capturing the consequence of that interaction. Okay, so we'll get into that in the next lecture. Bye.